Good morning, everybody. Welcome to our machine learning seminar. It is the seminar number 84. And today we have a pleasure to have presentation from Dr. Panos Pantidis, who is a postdoctoral researcher or research associate at the New York University in Abu Dhabi. Panos, the virtual floor is yours. Please say a few words about you and then follow up with the presentation.
Great. Thank you very much, Jacob, for the introduction. So yes, my name is Panos Pantidis. I'm a Greek guy. I'm working right now for NYU Abu Dhabi. I did my PhD at the University of Massachusetts in Amherst. And then I moved to New York. I worked for a consulting firm called Thornton Tomasetti. So I wanted to take the flavor of the industry before I returned to the academia again. Now my focus is on, my research focus is on computational mechanics for multi-physics problems. And actually this presentation is about I-FENN, a framework that me and my advisor, Dr. Mustafa Mombasser, we are slowly and gradually building up to target these kind of problems. So the title is Accelerating FEM with Machine Learning, and then the name of the framework, which is Integrated Finite Element Neural Network, shortcut for I-FENN. And the goal, and this is what I always like to begin with, the goal is to accelerate FEM. So this is the end target at the end of the day. First of all, let's begin with why we care about these things. As an engineer, I have seen in practice myself that sometimes we're facing problems that are very challenging. We have multi-physics problems, multi-scale, non-linear, non-local, and numerically discretizing for all these kind of problems. We know that it will lead to the creation of a very large degree of freedom vector and consequently a very large Jacobian. And from a computational standpoint, it is the repeated inversion of this large Jacobian that takes the most time in the FEM simulation. So ideally, we would like to decrease the size of the Jacobian while still capturing all these characteristics. So we asked ourselves, can we somehow use machine learning to help us do this? And this is the kind of thought process that led to the birth of I-FENN, which was published in CMME, the first paper, the first part in October 2022. We just published actually the second paper, I think 2 weeks ago, again in CMME, it was accepted, and we are building towards that. But we need to keep in mind that this is a multi-staged process, and we are now on staircase number 1, on the first stair. So the idea behind I-FEN is the following. The core idea is that we split the governing PDEs into 2 categories, FEM and machine learning. FEM will take care of some of the PDEs, in particular the equilibrium, which means that we will solve numerically at each node for the displacements, and therefore we will preserve compatibility, and we will ensure that we have numerical convergence, which is the guarantee that our results make sense. And at the same time, the machine learning model, and in this case we're using a physics-informed neural network. This is the tool that will target the additional PDEs. For example, the case that I will be talking about today is about a non-local strain transformation, but in general, we can apply it in other cases such as thermoelasticity, porosity, and more. And the key point is that these 2 methods, FEM and machine learning, PINN, from henceforth I will be calling it PINN, work in conjunction with each other. They act synergistically. They communicate, they exchange information, they don't act separately, because at the end of the day, we don't want to replace FEM. We just want to strategically intervene inside the FEM loop, plug in appropriately the PINN, and see what will be the benefit. And the schematic can be seen on the right. So once we begin the analysis, we will solve for the displacements using FEM. This is the first step here. By the way, can you see my cursor when I'm pointing?
Yes, we can see it.
Right, okay. And then we will dive into the element level stiffness function. And then we will use the pre-trained PINN. We will feed it the displacements. We will compute the other state variables at the Gauss point level, not at the nodal level. This is the key difference. And then the output of the PINN, we will use it again with shape functions, the material model, and other FEM procedures to construct the Jacobian and the residual. And then we will check convergence, and we will preserve both the iterated loop and the low decrement loop until we have convergence. This is the idea of I-FENN. And as I said, we can apply it to many multi-physics problems as long as we have the equilibrium and something else that can be fed from the equilibrium. And in this case, today I will be talking about the first problem, non-local damage. But we can have, other types of problems more challenging down the line. So now that we have the general idea in our head, let's begin with the more technical details. And first, let me give you a background on continuum damage mechanics. So in CDM, continuum damage mechanics, we represent the crack in a body in a continuous way. This means that we assign a variable d at each point that represents the magnitude of the stiffness loss. If d is 1, we don't have any damage, it's an intact material. If d is 1, we have a fully damaged state, and d will take values between 0 and 1. In the local damage approach, we calculate the displacements at the nodes, then we go to each Gauss point separately, we compute the strains, and then the damage based on the appropriate damage law, and this is the most cost-effective approach that we can. The problem with the local damage method, displacement, strains, and damage, is that it's mesh dependent. This means that for different mesh idealizations, we will arrive at different solutions. And for example, here on the bottom left, I'm showing you a simple single notch problem. I'm using 3, but I'm only showing the results, for 2 on the right mesh sizes. And for a coarse mesh, for larger elements, we have the green curve. We don't see any reduction in the curve. But for the fine mesh, the smaller the element size, we actually have a much smaller capacity. This means that different mesh will give different results. This gave birth to several non-local formulations, and one of the most prevailing one is the non-local gradient formulation proposed in almost 30 years ago by Perlings that essentially adds this additional PDE. And this PDE is an equation that makes a transformation between the local strain, epsilon EQ, to an equivalent non-local strain that essentially has an idea of what's happening in the neighborhood of that Gauss point, and it makes this transformation through this Laplacian operator. Now, if we discretize numerically this PDE inside the finite element solver, we will arrive at this additional degree of freedom, the non-local strain at each node. And of course, we have these 3 additional terms in the Jacobian. This is what I said before, that the more PDEs we add to the problem, the larger the Jacobian, and therefore, ideally, we would like to have something that solves only for the displacements. Therefore, we have only that first term, the J, but we don't miss any information of what's happening in the non-local quantities, in the non-local strain and the non-local damage. So moving on to how I-FENN was implemented in this problem, I'm sure you have understood so far that FEM will target the equilibrium and PINN will target the local to non-local strain transformation. And currently we have 2 steps. First, we do an offline PINN training to learn this transformation, this mapping between the local to non-local strain at this Gauss point. And once the network is trained, we take it, we plug it inside the finite element stiffness function, and we preserve that loop that I described before. And you can see on the, of course, I will go into more details in the next slides for both, but you can already see that the input of the PINN will be something that knows deformation information, right? Deformation information, the local strain. And the output is the non-local strain plus some partial derivatives. And you will see in the next slides how we use them. But right now we have 2 steps, training offline, and then use it in the online version iteratively within the solver. So first, let's talk about the offline PINN training. For those of you who are not familiar with PINNs, the central idea is that you don't use labeled data to guide the objective function. We use a governing PDE, and we're trying to minimize the residual at the collocation points. And in our case, the collocation points are the Gauss points. So the input for the PINN that we are using are the coordinates x and y of each Gauss point. G is a material length parameter that essentially states how diffused our damage is. And it's a constant in our case, but it may change for larger scale problems, so we still keep it as an input variable. And we have the local strain, of course, in the input layer. I'm only showing a schematic of 2 by 2, 2 layers with 2 neuron seeds, but of course the PINNs that we're using are much larger. We use the tan H hyperbolic tangent activation function, and the output are the following. First, we have the non-local strain, of course. And then we have the first and second order partial derivatives of the non-local strain with respect to the coordinates. Why? Because we need them in the governing PDE. You can see on the top right that the governing PDE that we need to minimize takes the second order partial derivatives of the non-local with respect to the coordinates. And we also have the partial derivative of the non-local strain with respect to the local. Let's put an asterisk on this. I will come back to that derivative in the next slide, why we need it. We don't need it for the training, but we need it for the iterative solver. So a few comments on that slide. Using either TensorFlow or any platform right now, it's very easy to compute these partial derivatives thanks to automatic differentiation. So number one, we use automatic differentiation. Number two, as I said, the collocation points are the Gauss points, but we also have this additional boundary condition at the nodes on the perimeter of the domain that we're analyzing. The loss function takes the L2 norm of the two governing equations, and we don't have adaptive weights or any kind of weighting between the two terms. We have a multiplier of 1 in both cases. We don't use any labeled data to guide the solver. We only use these PDEs as the objective function components. And the last thing that I want to say is that the local strain values actually are very, very small compared to, let's say, the coordinates. They are in the order of 10 to the minus 3 at max, minus 8 at minimum. So it's very hard for the network to actually deal with these kind of numbers. It can, but it's a little bit hard. Therefore, we multiply all the field of strain with a factor of 10 just to increase it, like a simple scaling effect. And then, of course, we will divide with the same factor later on. This is just as, to push a little bit and help the network train faster. Moving on now that we have done the training, we know the local to non-local strain. Therefore, we can go to the next step, which is embedding the trained PINN inside the FEM solver. We begin with the strong form, and of course the FEM discretization, we are using the shape functions and the derivatives. This is standard techniques in the FEM. The expression for the residual, we arrive at this expression of the external and internal stresses. Again, this is pretty known stuff. I am terming that second term here as K. This is what it's typically being called. We have the external component and the internal component. Everything here, N is the shape functions, T is the traction, so we know it, but we are using displacement control, so this is actually 0. B is the shape function derivatives, CIJKL is the constitutive matrix, and D is the damage variable. And we know damage variable, the D, because since we do the training, we know the non-local strain, and it's the non-local strain that we feed into the damage law to compute the non-local damage. So this is, we know how to compute that term. For the Jacobian, we have partial R over partial U, which means this goes to 0, K plus partial K over partial U. The first term, I just described it. We know the damage because then we know the non-local strain and we plug it into the damage model. The actual question is how do you compute the partial K over partial U? And to be more specific, how you compute partial D over partial U. And to compute this term, we use the chain rule essentially, and we're trying to represent all the steps that take us from the nodal displacements to the damage variable at the Gauss points. And this arrives, this led us to the following expression. We have these 4 terms, partial D over partial non-local strain, partial non-local strain over partial local, local to tensorial, and tensorial strain to the nodal displacements. How do we know each one of them? The first term is the dependence of the non-local damage to the non-local strain. We know this because we know the damage law, therefore we can take very easily the derivative. The partial derivative of the non-local strain with respect to the local, it's that asterisk that I put on the previous slide. This is the second output of the PINN. Remember, we know the non-local strain and some partial derivatives. This is why we need one of the two, because we need to close the loop. The third fraction is again known because we know how we have defined the local strain based on the tensorial components. So this is also known, and this is nothing more than the B matrix. Which means at that stage, we know J, Jacobian, we know the residual R, therefore we can compute the displacements. And here I want to highlight once more, J is in the order of just the displacements. So we are able to decrease the number of j. At the same time, we do have all this knowledge about the non-local strain and the non-local damage. This is what I meant, decreasing the size, but still keeping the physics alive. And as an overall comparison method, a comparison table of the methods, here I have the local, the non-local gradient, and on the third column I have the I-FENN. I don't know if you can see the window that I'm seeing, or if you can see the entire slide.
We can see the table and no additional window.
Okay. I try to shrink even more. So the key takeaway from that is that, for an n, if we have n nodes for a 2D problem, in the local and in the non-local, in the local and in the I-FENN model, we will have 2n degrees of freedom, and the Jacobian will be on that similar size. On the non-local gradient, we will have this additional degree of freedom, these more expressions, and this is where the savings are coming from. So this is about the math. I hope you have stayed with me so far. Henceforth, it's the results of the implementation. So the first test case that we're doing is a single notch. It's a pretty standard problem in fractional mechanics and damage mechanics. I'm only analyzing the upper half of that geometry under mode 1, and I'm restoring the symmetry boundary conditions here. We are doing 3 different mesh idealizations. I'm calling them coarse, intermediate, and fine. I'm just changing the size of the element, and you can see the idealizations here. So this is the coarse, this is the intermediate, this is the fine. And to make sure that the non-local solver that we have developed in-house is yielding mesh objective results, the first thing that we need to do is to plot the reaction displacement curves. They overlap, so yes, they are mesh objective. And here I'm also showing the snapshots of damage at these load increments of interest at 0.7 and 0.82. So again, the picture is the same across all 3 domains. So now we will see, now that we have the trust in the non-local gradient solver, we can compare it with the I-FENN and our framework. Now I need to make an important note. In the results that I'm going to show you from the next slide on, we are making predictions on each time step separately. So for example, this slide corresponds to the results at the first load increment at L factor 0.42. Here you see on the top left the true non-local strains from the FEM. This is the field. And here you can see after we do the training how the non-local strain field from I-FENN looks like. And here you see the relative squared error between the two. And the color bar is capped at 0.005, so at a very, very low value. And here on the right, you can see the hyperparameters that we have used to train the network. And we can see that, we are able to capture the mapping from local to non-local very well, and this is verified by the relative squared error. Even more importantly, when we do the I-FENN solver, we have convergence, and this is the most, the most important thing. I mean, you can train a network to make transformation, but actually plug it inside the solver and see the residuals converging, this is the real challenge. And the red line in both graphs corresponds to the internal stresses residual, and the blue line corresponds to how the incremental change of the displacements looks like. And the criterion of convergence is that the blue line from the first to the last value has dropped at least, I think, 6 or 8 orders of magnitude. And in both cases, we see convergence both for the internal stresses and for the residuals of the displacements. This is still in the elastic regime, so there are no damage results. But if I move to the next load factor increment, again, I have the true on the left, the predictions in the middle, and the relative squared error on the right. The top row will show you the local strains, and you can see that we capture them pretty accurately. And this is for the non-local damage. So this is another layer of comparison between the two methods. Again, we are very close. The reason you see this white space, it's because it's 0/0, so it's non-defined. And again, we have the convergence of the residuals at the bottom row of this graph. And a similar picture, I think, is for the 0.82 on the next slide. Again, we have pretty good accuracy both in terms of strains, damage, and convergence of the residuals. Something important that probably have attracted your attention. You see this region of higher values. This is actually the least significant region in the model. This is where the crack begins and it propagates towards the right. Right before the crack tip, the strains are extremely small. So the area that the strains are important and guide the problem is here, where you have 10 to the minus 3. Over there on the corner, you have 10 to the minus 7 or 8. So it's very difficult for the network to predict, to distinguish between 2 times 10 to the minus 8 and 3 times 10 to the minus 8. This is why the higher relative errors, you will find them in this region, but this region is essentially not even loaded. So all I'm saying is that, we really care about what's happening in that region, which is at the crack tip and ahead. And now that we have, established some confidence into the principles that, at least it's working, we wanted to see and scratch the surface. We're not doing an in-depth investigation. We're only scratching the surface in some directions that we find interesting. So the first thing, and I think this holds some strength for the future, is to be able to generalize across different meshes. So the idea is, can we train a network on a coarse mesh, very fast, and then use it and plug it and apply it in finite discretizations. So imagine the savings not only from the degrees of freedom reduction, but also from applying it into a mesh that it's much finer. And the results so far indicate that we actually can. So here we are training on a coarse and we are testing on intermediate. So all the plots that you see here are of the intermediate, but the network has been trained on a coarse mesh. And for all the load factors of interest, 42, 0.7, and 0.82, we get very good correspondence between the true values of the strain and the predicted, and this can be shown in more clarity on the relative square term. So this is generalizing across the meshes, but for the same load step. And of course, yes, we did it for the fine. That's another slide. The same principle, trained on coarse, tested on fine. And the second direction that we wanted to see if there is, and promising results, is whether we are able to generalize across different load steps. So we are using the same mesh. We're using the coarse mesh, I think, in this case. Yes. And we are training it on 4 load factor increments, 0.1, 2, 3, and 4. And we are testing on 0.25. I know this interpolation. I know that this lies in between the range, but we need to do baby steps. We cannot jump to grand conclusions without having verified that, we have reasonable accuracy in this case as well. And by the way, this hasn't seen any data at all, and it's conceptually challenging to see if we can actually have convergence and without any information on that particular increment. And we can see that actually we are able to predict very well. And here I'm actually zooming in to show you on a Gauss point per Gauss point basis how the nonlocal strains look. And the next thing is that we did it for the inelastic regime, which is even more challenging. We're training on 5, 6, 7, and 8 and testing on 0.65. And you can see that, yes, in that region where we have the lowest strains, we don't get the best of the accuracies. But in the area where damage is being initiated and drives the problem, we are actually able to capture it. And of course, this is just scratching the surface. There are even more suitable tools to make, predictions over the load history. And actually, this is what we're working on right now in more depth. All this was in one geometry. We applied it in different geometries. I'm not going to stay on the same level of detail now that we have seen the details on the single nodes, but I need to show you the results that we have validated the results in other geometries. So the second was a double nodes, again under mode 1, still structured mesh, 2 mesh discretizations, coarse and fine, overlapping reaction curves, same qualitatively and quantitatively non-local damage snapshots. These are the results for the first load factor at 0.45, and this is for 0.7. On the top, you see the strains. In the middle, you see the damage. On the bottom, you see the residuals between the FEM and I-FEN. So the true on the left, the predicted on the right. And you can see that they are very close to each other. And we also did that for another geometry, for an L-shaped geometry. Here we wanted to see how it will perform on an unstructured mesh. So here we expect the damage to grow in this direction. And we wanted to see if we're able to train on a mesh that looks like this. It seems that we can. Again, the same layout, two load factors, true on the left, predicted on the right, strains, damage, and residuals. And in all cases, we are able to achieve convergence, both for double nodes and the L-shaped. So I think this concludes the main points that I wanted to discuss in this presentation. And I hope I'm okay with time. I think I'm around 26 minutes. Great. So if we actually have more time, I have some more slides to show you, but they are on the next effort that we did, if you're interested. But so far, I want the takeaway messages to be the following. We have developed a new approach of integrating PINNs into FEM because we believe that we can enhance it, but still we need to maintain the umbrella of robustness that FEM provides us. It has been a long-standing method for decades, so we don't want to discard everything and then just throw it away and plug machine learning to replace it. We want to use and take advantage of the best of the two worlds and make sure that they are always in communication with each other and we always see the residuals converging. This is why I'm highlighting it again and again. So this is the approach, and this is just the first stage. Eventually, we would like to target even more complicated multiphysics problems with more PDEs and make predictions over time. But for now, we have developed it for the case of non-local gradient damage. We applied it in several geometries, different mesh sizes, different mesh orientations, and we have seen promising results. So that being said, this concludes the presentation so far. I may have some hidden slides if you're interested. Thank you very much.
Thank you so much, Panos. It was a very interesting presentation indeed, and and the method that you showed. So I believe there might be some questions. I have a few, but I will give a chance to others first. If anyone wants to ask question. Yes, I can see Sorab and Vasily. So let's give a chance to Sorab first.
Hi, Panos. Really nice presentation. Quite impressive work.
Thank you very much.
Can you please go to slide 10?
Yes.
Yeah, here I wanted to ask. So let's say I suppose that you're trying to predict the U with your neural networks and then eventually calculate the residual and derivatives of residual, right?
Not quite. So the first part of the sentence was not correct. If I heard you correctly, I think you said we want to predict the U. We don't want to predict the U. We use the U, the displacements at the nodes that we compute from these terms, and we compute these terms based on these equations.
Okay.
But we don't predict the U. That's the key.
Because my question was, do you have problems, let's say, in the very initial training phase where you can have these ill-conditioned stiffness matrix and because you said that you do not use any label data at all and you're really off from your initial U value. I don't know if I'm able to frame my question correctly, but
let me put it this way. If I understand correctly the question.
Yeah.
We have seen problems with training on PINNs, and we have seen failures of training, complete failures. Actually, before we migrated to more complex problems, we decided to look into these things.
Okay.
And this is where the second paper is all about. So we have done a lot of work on seeing how the errors converge and what are maybe, you know, chances of training failure for the pins. But to answer that question, in this case, in the cases that we have that I showed you, which are not at the very when you say initial, you mean initial in terms of load increment, you know, first or second load increment, or at the beginning of a training?
At the beginning of training.
Okay, no.
Okay.
We train for a sufficient number of epochs, and probably this answers the question, because, you know, the more epochs that we saw that we were training, in general, we got better results. So yes, if we had stopped the training at 200 epochs, we would not be able to arrive at a good mapping between the two variables. But we train it for some thousands of epochs.
Okay. But yeah, thanks a lot. I look forward to going through the paper, and maybe
Yeah.
I hope it's okay to get back to you if I have some questions.
Absolutely, absolutely.
Thanks.
Yes, I forgot to mention that, but, you know, we're always open for questions, collaborations. You know, we are here. So thanks for the question.
Thanks a lot.
Vasilis, please go ahead.
Thank you, Jakub. Thank you very much, Panos, for the very interesting presentation. I do have a few questions to ask you. First of all, can you comment on the speed up that you get using that method?
Mm-hmm. So thank you very much, first of all, for the interest and for the question. The speed up, I have to say that it's always relevant to the problem that we are targeting. In this case, we are still far away from realizing the true benefit. Because for two reasons. One, we are doing the simplest case where we only eliminate 1 degree of freedom. We go from 3n to 2n. That's one. And the second, and actually even major, even more important component, is that we're doing predictions on a time step basis. So essentially, the gain at that stage is how faster we arrive at convergence at one load increment between the two methods. So still, we are far away from realizing the true potential and gain. Eventually, but we cannot begin with the time series predictions if we cannot see that we are doing well on a snapshot by snapshot basis. Eventually, when we make predictions, and I don't know why this GIF file didn't play, but yeah, okay, now it does. This is what we're working on right now. How we can make predictions over time and see, you know, the convergence over time, and then measure the computational speed up. This is, you know, probably if you ask me that same question in about a year, hopefully less, I will be able to give you even numbers.
Okay.
And excuse me, I just remembered of a third component. You see that the residuals do not decrease and do not converge in the same number of iterations. So we need a different number of iterations between the FEM and I-FEN. In this case, actually, I think this is the only case. Okay, my bad luck. I'm showing you that it takes more iterations,
Sure.
but in general, we saw that it takes either the same, okay, this is more, this is the same, or less. I think that in the single course, single nodes, it takes less. So there are several things that contribute, but the major is the degree of freedom elimination and the time series. This is where and this will be realized only down the road. Here we're just still, you know, seeing if this is feasible or not, if this makes sense or not.
I see. Thank you. But I guess no way this is going to be real time, right?
It's still an FEM simulation.
Yes, exactly. Okay. Thank you for that. Okay. And can
Yes.
you comment about going to 3D cases? Like, what do you expect to happen about this? Okay, not about the speed up, but about the complexity of how to apply your method. Is it just going to be the same, just different equations?
It depends on the problem. If we are talking about non-local gradient damage, where we may have an isotropy in the 3D case, it's not going to be straightforward. But the problem itself, even without I-FEN, would be 1 or 2 orders of magnitude more complex. So the idea is that we don't try to. It's like a computational framework that gets adapted to each problem that it's dealing with. It's not that we are taking away any of the constitutive laws that make it more complex. You know, we try to adapt to what we find and just see if we can do quicker and at the same time, at least at the same level of accuracy. I don't know if this answers the question.
Yeah, it does. It does. Okay, thank you. And last question. You mentioned that you scale by 10 your data or something like that so that the network converges easier. Just a suggestion then, why 10? Why don't you use the statistics of your data set to scale it to values with a maximum, like from 0 to 1 or something like that?
So we tried okay, you're talking about normalizing with min-max?
Yes, or just scaling with the max value or the mean value or something like that.
A few comments. Actually, the 10 that I said was for the inelastic load increments. For the elastic was 100.
Okay.
Just as a point.
Yeah.
We did try the statistics. So we did try the average value. We did try the other multipliers. And actually, right now that we're doing on predictions for the entire time series, we are adjusting also that multiplier. We didn't find better results, to be honest, when I scaled it with the average. I don't know why. I'm not that aware of why I didn't train that much. It did train, but I think that the quality of the results was better when we just scaled it with a factor of 10. And we arrived at that by trial and error. By no means we had an a priori knowledge. This is still new to us as well. So we tried a couple of things. We saw that this is working better than the other. We didn't dive into too much detail. We said, okay, let's stick with that and focus on the conceptual stuff. And now when the time comes that we will try to improve it and make it more efficient, that's one of the things that we are still keeping in our minds.
I see. Okay. Thank you very much for your answers to my questions and for your presentation.
Thank you very much.
Thanks, Vasilis. And now I think Andrei was the next in the queue.
Yeah, thank you. Do you hear me?
I can hear you.
Yeah,
yes.
Thank you very much for this interesting presentation. I have a question about your neural network architecture. So do you use only fully connected layers? So you just took like 10 layers and it was enough in your case. And the next question is, have you tried any other architecture, maybe even CNN for this type of problems?
So first of all, thank you for the question. We are still using the MLP in this case. So for the first paper and the second, we are doing the fully connected architectures. And again, this is by in the first paper, it was blindfolded. Let's increase, let's decrease, trial and error. We didn't have an a priori knowledge of how each hyperparameter of the network will affect, which is exactly why in the second paper we did a study on exactly this. So in the second paper we had an error convergence analysis and the hyperparameter search that would build this a priori knowledge. So I can give you more detailed answer on the hyperparameters if we go to those slides as well. But to answer the question, yes, it's an MLP with trial and error. This is how at that stage we had arrived in this configuration. To answer the second question, since this is just a snapshot basis comparison and we're not doing predictions over time, we didn't see value in using RNNs, for example, or GRUs, even though since this is like an image that you can see, a CNN perhaps could be suitable. But we need to keep in mind that this was also our first attempt. We want to start from, we want to always increase complexity. We don't want to start from somewhere and then realize it's not working and then go back. So we always want to start from the bottom and go up. Now, when we go to the time predictions, as I showed you here, now this is based on a physics-informed TCN, temporal convolutional network. We have seen that it holds some, promise at least for these types of problems. It can be trained quite well. By no means I'm discarding other techniques or other tools, But right now, the third paper is focusing on using PITCNs, physics-informed temporal convolutional networks.
Okay, thank you.
Thank you.
So we have a question in the chat from Monsieur Didier. I don't know if you want to ask it yourself or I can just read it out. Okay, let me read it. In the case of highly nonlinear analysis involving large deformations, what will be the challenges or limitations of your approach? Could it be used with any FE solver like explicit dynamics and show advantage in terms of CPU time? You may.
Yes, that's a very good question. So my answer to this is that there are other techniques that you can use to decrease the time. By no means that's the first one. I mean, you can use staggered schemes, you can use explicit solvers, you can use different approaches. Since we haven't realized the full gain of this method, it's hard for me to predict what would be, a tangible number. I expect it to be what I expect to be harder for our case is the training of the PINN and learning that transformation between the input and the output. I expect that to be harder when we go into higher nonlinearities. Why is that? Because I mean, in the elastic regime, you just scale, essentially, you scale everything. So if I look on this reaction curve, if I do the training and the transformation from here to here and here to here and here to here, it's just a scaling factor. Qualitatively, the strain field will look the same. Now, when we go to the nonlinear regime, the strain field on the input will change fundamentally, significantly. So I expect it will require some major rethinking and improvement of the tool that we're using. I don't know if we will need to use a transformer or transfer learning. To be honest, I think that transfer learning, but this is just a guess. Anyway, it is a feeling. Let me put it this way. I think that transfer learning could be a potential tool that will alleviate that problem of having a different input field all the time. But since we haven't touched that yet, I know that this is not very satisfactory, but I cannot give you a more complete answer than that. I expect the training, though, to be harder. I do it. I do expect it. And I see the transfer learning to be one of the potential tools to overcome it.
Thanks a lot for your answer. Thank you very much for the interesting presentation. Now, what prevents you to you use a Newton-Raphson or, well, a static solver on your example? Would it be interesting as a next step to use an explicit solver? So you would increase significantly the number of critical time steps and see also how your algorithm is performing there.
Thank you for the suggestion. I mean, I don't know if that was a question or a suggestion. I think that it was a suggestion. If we are using Newton-Raphson, we are thinking of going to explicit solvers. And again, there are so many things to be done that we always need to start from somewhere. So for now, we have developed that in-house solver. It's using the Newton-Raphson. We just actually recently developed an displacement arc length method for damage, which will take us to even more challenging problems with snapbacks and snap-throughs. But it's still implicit for now. In the future, who knows?
Mm-hmm. Okay, thank you.
Thank you.
Okay, maybe let me ask a question. It will be a comment, maybe, and a question hidden in the side. So, so you are using this non-local gradient damage model, which is somehow approximated by the neural network model at each ghost point. So you, in the gradient-based damage model, you have an additional degree of freedom per node that needs to be introduced, and it has been introduced in order to somehow regularize the damage model. This was one of the purposes of using gradient-based model. And in your case, you're approximating it with neural network, which somehow reduces the dimensionality of the problem per node into the original 2 degrees of freedom in 2D case. And the comment is that, by the way, this gradient-based damage model, it has been shown that it is not even compatible. It is equivalent to the phase field regularization. It has been done in, I think, 2016 by De Boers. So it is a nice way to look at the problem from a bit different perspective. So we have this diffused damaged parameter that not only captures the 0 and 1 values, but also the spectrum in between. So in that term, my question would be that originally one of the intentions was to regularize the damage, meaning that you have this path dependence that is regularized and you are able to capture this post-critical path beyond some critical strain level. And now you're removing this degree of freedom that was able to hold it originally. And my question is, have you checked how your method influences the problems with the solution in the time-stepping scheme, or when you increase the load, whether it performs well enough or similarly with the original problem? And I'm not sure if I was clear enough.
So I think I understand the question. Let me take you to that slide. It's the first slide of the results. In terms of comparison between the two methods, we see, for now at least, a reasonable agreement. I would call this at least reasonable agreement. Again, this is on a time-step basis. How it evolves, as I said, it's still to be discussed and to be actually investigated. We haven't touched we haven't worked in that depth yet. We are working together. We are working right now on that time-step prediction. So this is when probably we'll be able to answer better that question that has to do with how you regularize over time. Just a comment on the phase field, which is very, very similar to that. It is down the road to be. We have made a plan, and I think that phase field will eventually go to that as well. I'm not sure if I answered your question, because I know that this is like in terms of comparison, the only thing I can say is that on a time-step basis, it seems that it's working. It's giving us convergence and good predictions both for the damage, and we need to remind ourselves that we don't see any damage in the strain in the PINN. So we're using something that we're making a transformation between local to non-local, but we don't plug any damage model in that training, and we're still able to capture that quantity. So this is how we say that okay, it's working. Now let's make it more challenging. I don't know if this answers the question, or if not, of course you can rephrase it or.
No, I think that you have answered the question even before that. You mentioned that it is a first step into the longer process of investigating this approach. But my comment was towards that perhaps this is a time dependent or a path dependent problem, and then you are removing one of the parameters that controls this evolution over time. And the question is how this influences the solution and the convergence properties of your approach.
Let me just say this not as a caveat, but as an observation that I made during that phase. One of the drawbacks is that we need to train a new network for the time being, for the time that paper was written. We had to train a new network for a different load step increment. which means that, you know, one was not sufficient to, by its own, to learn such a hard task, you know, to reflect the path dependencies and make it, you know, make reasonable predictions. Which is why here we are introducing this component of time into the PyTCN. So PyTCNs are essentially convolution with a temporal component, and we are evaluating the PDE in this case across the entire load history. So we are in this case that I'm showing you. I mean, it's not the case; it's just an image, but it reflects the following this attempt. We are training over time, which means we, at each time step, we are introducing the local strain quantities that has changed from the previous ones, especially when we're down in the highly nonlinear zone. We are still able to see reasonable, more than reasonable agreement, but we haven't yet taken it into the FEM solver and see convergence yet. So we are kind of 60-70% of the first step of the offline PINN training. This is where we are right now to answer somehow your question. But you are absolutely right. Using the MLP in the way that we have done it, it cannot. It's just too weak to reflect the dependence over time.
Okay, that's a clear enough answer. Thank you so much.
Yes, thank you. Yes.
I think I cannot see any more questions in the audience. So let me thank you again for the presentation and for answering our questions. And let me welcome everybody for the future machine learning seminars. I will keep you informed about the incoming meetings, the upcoming meetings. And for today, have a good day and bye-bye.
Thank you very much. Thank you very much.